Hey physics students, I'm on page 82, and this is introduction to vectors. All right, this is Unit 2, Chapter 3, page 82. All right, vectors indicate quantity and direction. Scalars, on the other hand, are scalars only indicate magnitude. Scalars indicate magnitude only. Displacement and direction are two examples of vectors because they indicate magnitude and direction. We talked about those in Chapter 2. The length of the vector shows magnitude. The length of the vector shows the magnitude. So here's an example of a vector that we could call A. There's one. Your book will have these in it, and in boldface. However, just a line over it with an arrow is another indication that it is a vector. So let's say that A equals 80 meters, or 8 meters. And then we have another vector that indicate, and we'll call this one B. And we'll say that one is 3 meters. Well, clearly, in this one-dimensional image here, we could have a third vector that shows that we go back to where we started from. It shows us going back to where we started from, and that would be, we'll call that one C, and that could be 5 meters. Well, clearly these two vectors are negatives, and so we're right back where we started from, and so this is vector C. So we might also ask if vector A minus vector B equals vector C, and vector C would be considered the resultant vector, because it was the product of the previous two vectors. If we decided to multiply the vectors by 2, then 2 is our scalar. Right? So as you can see, the length of the vector indicates its magnitude and also its direction, because we could say this is north, south, this is west, and this is east. All right? This is another method of illustrating the same thing. We have parameters for our vectors. These are supposed to be evenly spaced. This is a scale of 1 meter. This is supposed to be a scale perfectly scaled to 1 meter. And let's just, for simplicity's sake, this is 1 meter as well. So if we start here, and each one of these is a vector, we're going 3 meters north. We've gone 3 meters west. Now the displacement is 3 meters north west, right? So that would be our displacement. That's another way of illustrating the same idea. What if two vectors are acting at the same time? What if two vectors are acting at the same time? Now, in that case, we might have an example of a boat. This is supposed to look like a boat, and the boat is traveling. And just for simplicity's sake, we'll just use a ruler. Let's say that our boat is traveling with the magnitude of 6 meters per second, and it just so happens to have a bit of a cross current. The cross current is acting, we'll say, at 4 meters per second. So the resultant vector in this case, we could simply measure to be 7 meters per second. Right. So all I did was I just measured it. All right. I know you can't read it, but so that would be considered. This would be considered the resultant force. That's the direction the boat will travel, given the cross current and the forward velocity. So the negative of a vector is the same magnitude but opposite direction. So the negative of this vector would be negative 6 meters. Of course, it would be going not, we'll call this north, south, east, and west. The negative would be not south but north, 6 meters north. Okay. And then, of course, if you add vector to its negative, you're just going to get 0. That seems clear enough. Let's take a look at the section reviews. Running out of time. The section review. I'm on page 85. Number 1. Acceleration of a plane is definitely a vector. B, the number of passengers on a plane is the scalars. Letter C, the duration of the flight is a scalar. D, displacement of the flight is a vector. E, the amount of fuel is a scalar. All right. So you can take a look at those questions, and now that you have the answers, and maybe it'll make some more sense. Number 2, a roller coaster. Now we have a roller coaster, and we're meant to do this with our ruler because it clearly says use graphical technique. We're not going to use math. And this roller coaster goes 85, and I'm scaling this to centimeters. So here's 8.5 centimeters, which is equivalent to 85 meters. And then according to this, it travels at an angle of 30 degrees above the horizon. So here we're going 30 degrees above the horizon. It goes for, I think, 45 meters. So we have another vector here, 45. And then the question is, what is the displacement? So the displacement would be the connecting the ends. And as you can see, it's 127. So this is 45, this is 30 degrees, this is 4.5 centimeters, excuse me, and this is 126. 126 or 12.6 centimeters. I was thinking in meters because that's what these are supposed to represent. That's what our book is using. A book is using meters, but we could easily translate it. So the answer is that the displacement is 126 meters. I just used centimeters because it was a scale that I could use.